All right, so let's talk about graphing quadratic inequalities. Suppose we're tasked with graphing the quadratic inequality x squared plus x is less than or equal to 2 times y plus 1. Recall that whenever y is expressed as a dependent variable in relation to an independent variable x, we consider y a function of x, which is to say, y equals f of x. Therefore, any quadratic inequality of the form y is less than or equal to ax squared plus bx plus c, such that a, b, and c are real numbers, and a does not equal 0, will also be a quadratic function. The inequality in question is a quadratic inequality in non-standard form. So the first action should be to rewrite the inequality in standard form as follows. Okay, so now that we have that done, recall that every quadratic function takes the shape of a parabola when graphed. The sign of the numerical coefficient of the squared term a will determine the projection orientation of the parabola, whether it's projecting upward or downward. In the case when the squared term is positive, the projection is upward. When the squared term is negative, the projection is downward. The vertex is the lowest or highest point of the projection, depending on its orientation. Let's have a look at some examples of the graphs of quadratic functions. Great. So we can determine the axis of symmetry, denoted by x equals minus b over 2a, of a parabola, at its vertex, denoted by the ordered pair minus b over 2a, representing the x value, and 4ac minus b squared over 4a, representing the y value of the vertex. So let's go ahead and plug in the relevant values in order to work out the axis of symmetry and the vertex of the inequality, which we've labeled Roman numeral 1 for convenience. Okay, so next we should locate any axial roots and intercepts that may exist. To find roots of an equation or inequality algebraically, set y equal to 0 and solve the resulting equation ax squared plus bx plus c equals 0 for x. Equations and inequalities of this form may be solved in a number of ways. We'll cover 3 of them. 1, by factoring if the trinomial is factorable. 2, by completing the square, and 3, by the quadratic formula. And so I'll probably do a video later on deriving the quadratic formula, deriving the formula for the vertex of a parabola, and so on. But for now, let's just assume that you may have at least seen it once or done it once, and we'll just, in the spirit of review, simply use and apply these formulas as needed. Okay, so the roots may also be found by graphing the function and finding intersections. This is a bit less reliable, a bit less precise of a procedure, but of course, with modern graphing calculators and graphing tools, we can do this quite reliably. But we're mostly interested in this video in the algebraic means for finding these points on a graph, on a quadratic equation or inequality. All right, so here we have, per the quadratic formula, the formula for x, which is found by taking the ratio of minus b plus or minus the square root of b squared minus 4ac to 2a, or over 2a. Okay? Now, we're just going to apply the discriminant property, which gives the number and type of solutions of a quadratic equation or inequality. if b squared minus 4ac is greater than 0, all right, if the discriminant is greater than 0, then the quadratic equation or inequality has two distinct real solutions. If the discriminant is equal to 0, then the quadratic equation or inequality has a single real solution, which is often termed the double root. Okay, if the discriminant is less than 0, then the quadratic equation has no real solutions, and we're in the world or in the realm of complex numbers and imaginary numbers and so on. Okay, we'll get into that more later. So let's determine by factoring if equation 1, Roman numeral 1, has any roots or real solutions. First, we'll use multiplication to set the numerical coefficient of the squared term equal to 1, as follows. Great. So now we've rid the equation of any fractions, and we have something a bit nicer to work with. And it turns out that x squared plus x minus 1 is less than or equal to 0. Let's see if this is a perfect square trinomial. So to factor trinomials of the form ax squared plus bx plus c, where a is equal to 1, the first step is to find two factors, or summons, whose product is equal to c and whose sum is equal to b. The factors of the trinomial will be formatted as shown here in parentheses. Well, clearly there's no such d sub 1, d sub 2 that are real numbers, which satisfy the inequality derived just above. And let's marginally observe that when the coefficient of the squared term is 1, there's an important relationship between the first degree term and the constant. Well, in every perfect square trinomial, the constant term is the square of 1/2 the coefficient of the first degree term, which is to say, c equals quantity 1/2 times b squared. When such a perfect square trinomial is written as the square of a binomial, the constant in the binomial is 1/2 the value of the coefficient of the first degree term in the perfect square trinomial. That is to say, x squared plus bx plus c equals quantity x plus b over 2 squared. Right. So to solve a quadratic function by completing the square, first, we use multiplication or division to make the numerical coefficient of the squared term equal 1. Then, we'll term rewrite the equation, or inequality, with the constant isolated on the right side of the function. And then, we'll take 1/2 the coefficient of bx, we'll square it, and add the product to both sides of the function. Next, we will replace the trinomial with its equivalent squared binomial. And then lastly, we'll take the square root of both sides and then solve for x. Okay, so if we have obeyed the laws of algebra and the rules of arithmetic, we should end up with x equals approximately 0.618 or x equals approximately minus 1.618 as our real solutions or roots to this particular inequality. Of course, we should check these solutions in the original inequality to be certain. And so we see, having done that, we see that y greater than or equal to x squared plus x minus 1 over 2 in standard form has two real solutions at these values. Okay, so finding the y-intercept involves a lot less computation in this case. We simply set x equal to 0 and solve for y as follows. Great. Now we have all the necessary components to graph the inequality. Perfect. So the basic properties and concepts for quadratic equations also hold for quadratic inequalities. This is sort of what you begin to realize as you work these problems. So finally, to graph a quadratic inequality, replace the inequality sign with an equal sign. Draw the graph of the equation derived in step 1. If the original inequality contains a greater than or equal to, or a less than or equal to symbol, draw the graph using a solid line. If it contains a greater than or a less than symbol, draw the graph using a dashed line. And then finally, select any point not on the line and determine if this point is a solution to the inequality. If the point selected is a valid solution, shade the region on that side of the line. If the selected point does not satisfy the inequality, shade the region on the side of the line opposite that containing this point. And we're done. All right, so hopefully this is a useful and perhaps somewhat illuminating review of graphing quadratic inequalities. If you like the video, please don't forget to give it a thumbs up, give it a like, and go ahead and subscribe and hit the notification bell for more videos like this to come. See you in the next one.